be that, but I interpret this funnily phrased question as that, and therefore the answer would be that, and then you could have written either A or B or whatever. Then I read all those comments. I didn't just simply look at what you wrote there. So mostly I think you did fine. I have a couple of people who got 90%, so it was not an impossible test. I had only 3 people in the whole class who failed. Out of 95, 3 people failed. So I assume that this test was doable. So I will put the answers on the web. Question 4. I would like to point out I didn't ask what happened to the stack. I asked what happened to the queue. So there was some confusion there. Explicitly, what happens with the queue called queue? Yes? And then you explain to me what happened to the stack, which is not what I asked. Question 7, I accepted either C or D. C is technically incorrect because it's not the proper code to do an insertion, but the unintended side effect was that there was an insertion. Okay. And yeah, those were the only funny ones. Yeah.
So what was the answer to C, where we had to find which one is the correct?
Question 2C, my answer was 5. Okay, let me go through the answers. A quick question.
What do you have to do in one day to have both answers?
Oh my word. I incidentally marked it as a 1, not as a 2. I just saw it. I just thought it was bad. That was my mistake. Right. Every single one of you who only got 1 mark at question 1A, take a photograph of your test. No. Make a paper copy of your test or the whole test if you want. Give it to Miss Daly, Lushavasya. Da. Give it to Miss Daly. She'll give me the whole stack and I'll update your marks. My mistake, I do apologize. Thank you for noticing. Okay. The rest of the memo will be on the webpage by this afternoon, by this evening.
Question 2C, with the question about the constructor. Line 5 as returned type. So,
did I switch them around? Half the class had it as 5 and 2, and the other half of the class had it as 2, 5. I didn't look at it too carefully. So you're also complaining about 2C and 2D. Right. Let me have a look at this again. Might even push the class average up to 70%. What a pain. Yes? Any more? Okay, good. If anybody asks any of you, where do you get these tests? They're in front of my office. Sorting. What do I do? What do I do when I take this stack of test papers and I want to sort them in order of student number? Yes? I look at it. Yes, I have a look. I take the next one. I have a look. I compare them. Yes? This is number 1617, blah, blah. This is 1758, blah, blah. I compare them. And if they are currently in the wrong order, I swap them. That is sort. That is all you do in sort. When you sort anything, how many of you play bridge or something? You have a deck of cards, you want to sort them, or you want to shuffle them. How do I sort? I have to compare and I have to exchange. Yes, compare, exchange, and that's all that happens. And you get very slow algorithms that does that. And then you get algorithms where we try to be very clever and we do either less comparison, fewer comparisons, and or fewer exchanges. And that is all there is to sorting, literally. So our cost model, we count compares and exchanges. But there are some algorithms that can sort without exchanging. Doesn't make sense at this moment, but when we get to that, we'll see that. And then we count the array accesses. So very low location level, not the abstract data type. Well, the level is somehow so that I can sort. So we always assume that you have an array. Why would we assume that all our sorting takes place on arrays and not on linked lists? Juffrou de Bruin. Ek ken nou jou naam, is baie gevaarlik. Hoekom sal ek sort op skikkings en nie op geskakelde lyste nie?
Want dit is vinniger.
Hoekom? Jy's reg. Daar's meer om deur te gaan, daar sit self vinger daar. Remember what she said was arrays are quicker. Why? Because I can go directly anywhere. If I have a linked list and I want to do sort, remember a linked list you always have to walk through from the front. I can never jump in a linked list. So arrays make sense on the low level. Okay. One of the things, okay, so now we know we're going to work on arrays. We're going to compare and exchange. So the API in the book assumes that there is but please note that the abstract data type that you use must be comparable. Yes, and you've worked through like integer is comparable, clearly is this one less than that. But what if it's a date? Now you have all I have an array of integers. Yes. So the question is, I am using in my template interface the less. When I do my comparisons, I always check whether A is less than B. What would my algorithm still work if that were less or equal? Under what circumstances might that have an influence? And the suggested answer was that, well, have a careful look. If your input data is already sorted, all the input data have the same value. So I have an array that's all initialized to ones. Then less might skip some work because the things are not less. But if it's less or equal, they will actually go into that thing that might exchange them even though it wasn't necessary. Yeah, so just have a careful look at less and less or equal, because if the input data is all the same, it might happen. You can say that is a theoretical possibility, because where on earth would anybody want to sort something where all the input values are the same? What about patient temperature charts? If people are not very sick, then all of them would have almost the same temperature. So you have 1 million input values, and most of them are equal. And then you have the ones where the patient is really sick and you actually get a spike. Okay, so over a large data set, you might have values that are almost all the same, and here and there there's an outlier, which is basically the same as almost all of them are equal. Okay. Right, sorting cost model, talked about that. Aha, extra memory. There are two things that we have to have a look at. In any analysis of algorithms, you have a trade-off. You have a trade-off between time and space. And you will see that throughout this course. Suppose I have an algorithm and I see that it is very slow. Time is bad. Yes, I want to make it more efficient. It is almost always the case that if you then increase the memory that you use, you can make the algorithm quicker. Yeah. For example, why would that be the case? Because you're keeping temporary information as you progress through that original array. Okay? So you use some extra memory, but you doing that, you can actually make a more clever algorithm that can be quicker. So yes, I can make it faster, but then I'll use more memory. So you will all the time see the comparison between algorithms. Yes, this is an efficient algorithm, but look how much memory it uses. Okay. And there's a table at the end of chapter 2, which takes every sorting algorithm and tells you how much extra memory it requires and what the execution time is in tilde notation. You have to memorize that table. Okay. But if you understand the algorithm, memorization is a difficult thing. If you understand the algorithm, then actually you don't have to memorize, it's just there in the code. Yeah. But in my experience, when you get new things, you first memorize and later on I just know it kind of thing builds up. Also, there's an interesting aspect of sorting algorithms, which the book calls, is this algorithm in place or not? So what does in place mean? You know that if you have a spreadsheet, you can sort on a column. You can also sort on 2 columns. So the first column would be sorted, and you can have a secondary sort column. Some sorting algorithms does not keep the order in which elements, duplicate elements, appear in the original document. So I might have an algorithm that's, suppose I have values 1, 1, 2, 4, and now I run my sorting algorithm on this. Yes. One would assume that this one goes there in my sorted output, the second one goes there, 2 goes there, and 4 moves here, right? Which means that these 2 duplicate values, 1 and 1, kept their respective in the sorted output. But sometimes when you devise a clever algorithm, it might happen that that occurs. Then the algorithm does not sort in place. Okay? Sometimes it's quite inconvenient if this happens in real-life applications. You want to keep the original order. Imagine timing information. Yeah, now your times are, you sorted on the patient name, and now the times where you made the measurements for the temperature is not in time order. And it's a bugger up. But you could use a very quick algorithm to do the sorting. Okay? So just keep that in mind. Types of data, we will always say, let's assume a randomized input on the one hand. On the other hand, what if the data is already sorted? 4 of them. Randomized, data already sorted, data sorted in reverse order, or duplicates. Yes? There's a whole lot of the data in this array that all have the same value. Okay? And the behavior of the different algorithms differ tremendously in terms of efficiency. So if you have an application, you have to ask yourself, what will my typical data look like? And then you accordingly choose the correct sorting algorithm. Okay? So the correct sorting algorithm is always dependent on what the data looks like for that application. Right? Okay, that's all the yabbity-yabbity-yap. So let's start sorting. Our first sort is selection sort. Do you all know what bubble sort looks like? Yeah. If not, go ask Wikipedia. I just assume you know it. Selection sort tries to be somewhat cleverer than that. What selection sort does is it walks through the whole array for I equals 0 to n. And I increases by 1. That was a mean one in the test because I becomes I times 2, so you all missed that it's not all, few of you missed that it's not quadratic. Anyway, sorry. Come back to selection sort. I'm going to walk through my array. And then for each value of I, I'm going to look through all the remaining elements. Yes. So I start at the beginning. Yes. And then I look through all the remaining elements to see what is the minimum value in the remaining elements. Yes, so I do the function min on this. And how does one min? Well, you walk through them one by one, and you have a current minimum. Yes, your current minimum is I. And then you say, is AJ less than AI? And then AJ becomes the new minimum, right? So I take each element. Then I look at the remaining elements. I find the minimum value in here, and I do my exchange. Okay. Yeah. So how many times do I walk through this array? Well, I'm going to do this whole thing for 0, and then I'm going to look at 1, and then I'm going to look at 2. So I move through the array at least n times with the outer loop. But I'm going to do more than that. So for the outer loop, I have n. And then for each of these n, I'm going to look at n minus I element. Yeah. In other words, how many comparisons? If I is 0, I'm going to look at n minus 1. If I is 1, I'm going to look at 1. I'm going to look at n minus 2. When I becomes 2, I'm going to look at n minus 3. And there's no jumping out of that loop, because to find the minimum, I have to look through all these elements. Yes? In other words, how many elements am I going to compare? Well, the sum of these. Yeah? And off you goes. So let's look at the comparison and the exchanges. Clearly, every time I do all these, I have to walk through all of these to find the min. Yes? When I do find the min, I have to compare that to A of I and exchange, possibly. Yes? So proposition says, select uses if total approximation is now, well, because if you look at the maps and you look at the sum, yeah, and therefore you get n squared upon 2. Okay? I think No, I have n elements, 0 to n minus 1. Okay. And blah, 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 blah. Then I do my exchange. Yes? Then I increases by 1 in the outer loop. Then I compare again with these elements and the min in the inner for loop. Yes? Finding the minimum and exchanging. Okay. If you look at it, trace of the code, suppose I have the input sort example, it's characters. So I0, so then I would walk through I0, 0. Then I look at I1, I2, I5, I6, which is A, I7, I8, I9, I10, and I find that I6 is the minimum. Yes, in the red, colored in red there in the second line. So therefore, I swap the S and the A. Good. Yeah. So it's not just simply n squared, it's a n squared divided by 2 because I add. Remember the maths in the first chapter? It's the sum of. And interestingly enough, of course, how many exchanges will I make? I make my exchanges, since my exchanges is not in the inner loop, it's in the outer loop, I make exactly n exchanges. I might exchange something with itself, but I still call exchange. Okay? You have to know the proposition, but not the proof. Okay. Miss Daly, I will mention where proofs must be learned for the test. I change it from year to year, so I'll yell at you to write it down. And before the test, you have to email me again so that I can put it all on the website. What what are the proofs for this year? Okay. Right. So let's just see. Why should I exchange things even if it's not necessary to exchange? Can I not improve this n squared thing somewhat? Okay. Wait. It's slow. Remember that lovely log-log plot? Quadratic is like bad. We're trying to move to logarithmic. Okay, so selection sort works. The beautiful thing about selection sort is the running time is insensitive to the input. What do I mean by that? Whether you give it sorted input, reversely sorted input, duplicate inputs, randomized inputs, you get n exchanges. Yes. Okay. Insertion sort. So let's improve selection sort because seriously, I want to get away from this n squared thing. And I'm seeing some unnecessary work there. So can't we try and be clever and do less comparison or less exchanges? And I'm going to give away the crown jewels before we get there by doing a more clever algorithm. I get to n squared upon 4 compared, which is 2 times better, yes, in selection sort, but 4 times better in terms of the exchanges. Okay, but it's still quadratic. Okay. So let's see how insertion sort works. I start with my outer loop, and I go through all my elements one by one. And then I have an inner loop. And the inner loop says start at the current position and compare 2 elements, aj and aj minus 1. And almost in a certain sense, yes, look at that. If aj is less than aj minus 1, what does that mean? I have something like aj is less than aj minus 1, so I know I have to swap them. So here my exchange statement moves into my inner loop, yeah? Which means I'm going to make less exchanges. I don't make n exchanges. I make an exchange if and only if the condition for that inner loop is true. Okay? So how do I conceptually understand insertion sort? The code is almost trivial, but you have to have a conceptual idea. I'm a logical, analytical, left-brain person. So looking at code just tells me exactly what happens. But many of you who are excellent programmers visualize this. And you have a picture of how it develops. So if you have I want to explain that in a visual way every year, but it doesn't gel for me. But you have to visualize, if you think in that way, visualize how certain values, how certain arrays would develop and change if you apply the algorithm. Okay, so two ways to look at it. The book tries. They do the visualizing sorting algorithms. I look at that and I go, huh? Doesn't make sense to me at all. But if you're a visual thinker, just have a look at this as well. But importantly, match the code to the picture. Okay? I normally match code to things like this. This makes sense to me. Numbers. But if you're a visual person, look at those pictures to understand the code better. Right. So we can see what is the essence, what is the difference, where does insertion sort becomes better? Well, note that in selection sort, what am I doing? I am at a position and everything to my left is sorted. Yes, that is true. So with insertion sort, everything to the left of the current index is in sorted order, but they're not in their final position. Selection sort puts an element into its final position in the array come hello high water, right? Because I take the first one, I take the minimum over the whole array. Clearly the minimum over the whole array is in the first position, position number 0, and that is its final position. Nothing can be less than that. Then I move up 1 and I look at this, the second largest value in the array, and I move it into position A1. So nothing can be less than this, so it's in its final position. This is not true for selection sort. Why not? Because I keep exchanging values adjacent to each other. Selection sort makes huge jumps. Yes, it swapped the A and the S as far as exchanges are concerned. Over here in insertion sort, I, in a certain sense, bubble down this thing. So let's have a look at the example. I always compare to adjacent elements to see whether I should swap them or not. And if you look at the code, I start my J at my current position I. J must be bigger than 0, and Aj and Aj minus 1 must be in the correct position. Yes? If not, I exchange them, and that loop executes again. So I take two elements at the point where I am. I compare them. If they have to be exchanged, I do exchange them, but then I must compare this element again with all the elements previously found in the array. Okay? So this part is unsorted still. Yes, I didn't have a look at it. This part is sorted before I start this inner loop. And then when I finish the inner loop, this part is sorted again. But I exchange adjacent elements and I can do it repeatedly. Does that make sense? But don't I then do more exchanges? Why do I only do n squared upon 4 exchanges? Because now it seems as if I might be doing more. Get your head around this. Look at the code. Look at the example. Look at the visualization. You must end up by tomorrow morning. Yes, because every night you go through your work. By tomorrow morning, you must have a gut feeling of the difference between selection sort and insertion sort on a code level, on a visualization level. Yeah, and the differences between them. So again, you need to know the proposition, not the proof. And very importantly, read the book, check for which types of input data this will work well. And when you read this, for heaven's sake, take an array of size 5 and sort it by hand to see why it works that way. Okay? Because of the tests, the test handout, I did not get to shell sort. I'll have a quick run through shell sort, but 5 minutes. Yes? So I need you to read through shell sort as well for Wednesday. Yeah? Because then I want to carry on to the new stuff. Okay? What do I have to know? You have to know the algorithm. You have to have a gut feeling of the visualization of the algorithm. I'll never ask it, but you know, you must just know how this algorithm works. How it works on different types of data, what the mathematical tilde approximations are, what the memory is.